I have been, interested in imprecise probabilities since I was a student. I've been doing IP and related work for coming up to about 6 years by now. IP is something that's always very, very close to my heart. I am a statistician by training and by trade. What I do today, a lot of the work that I do right now is it goes beyond imprecise probabilities, but I always find imprecise probability is something that has come up in different parts of my work that are broadly situated in what I would call data science properly, and those have always been an inspiration. And I want to share some of the thoughts that I've had, having accumulated from this 5-6 years of time with you. And SIPTA community, as I have come to know it when I was still a student, has been very welcoming to me, and I've learned a lot from every one of you, which is why this is all making it very, very special. So this is essentially borrowing and rephrasing the mantra of the SIPTA community, which is always to say that there is more to uncertainty than probabilities. Uncertainty quantification is really something that is at the heart of endeavors in statistics and more broadly in data science and applications and different ways of approaching modern day data-driven decision making. So uncertaintification is something that needs more than probabilities, and data science needs uncertainty quantification. And this is where I think IP holds really great promise for contributing to the broader endeavors in data science. And when I was a student learning about IP, this is something that has always had a very philosophical spin and sometimes almost historical, because a lot of the classic works on IP that relates specifically to inference problems were performed, back in the day, if I can say, and also, at least several decades ago. But these are really thoughtful work that tell us, especially thinking again from the statistical point of view, how there is really more to probabilistic modeling that we have to care about. Especially the probability language is not something that could be used to capture the structural kind of uncertainty that is intrinsic to what we do. And I remember, this was, when I met Teddy for the first time, and that was, I think, the year that I started thinking about IP. Teddy told me about the story of the Ellsberg problem, and that's one of the very classic examples that illustrate to people how ambiguity is really not something that is inherently captured, by the regular kind of probability that we use. So if we think about the classic kind of inference problems, IP really emerges mostly from the robust Bayesian framework, where epistemic kind of uncertainty about the prior and as well as about the data model, the likelihood, could be represented as sets of probabilities. IP has also found its way in robust statistics. Huber and Strauss in 1973 is the classic word that discusses how the Neyman Pearson, sort of essentially a Neyman Pearson counterpart to most powerful tests between, instead of point hypotheses, but rather hypotheses that are embodied by capacities of order 2. And the next point, the fiducial and the structural and the functional sides of inference, this is really where my training came from. I was a student of Art Dempster's, and I've spent years of time thinking about Dempster-Schaeffer theory and thinking about belief functions, and also the modern application of belief functions in inferential model, which is what something that Ryan and Van Hai have spent many years to develop this wonderful body of work that talks about the logic behind using predictive random sets to capture uncertainty that has the structural element. And there's also things that go beyond statistics, such as in econometrics. Economists care about partial identification. This is something that actually will come up later in the talk, that is also a great area where IP has found its power. And if we think about, and this is by no means a comprehensive literature review, but just thinking about some of the things that we have seen recently within our own communities. This Bolchinell paper, again, Ryan was part of the authors team that discussed the satellite conjunction problem, and from there motivated why without IP there is not really a possibility to talk about inference with confidence for all possible hypotheses. There is the example of using sets of probabilities, interval measured, interval valued probabilities to do more robust electoral forecasting. This is the work by Dominic and Jörg and Thomas, and it was presented just in the last SIPTA, which is a very fascinating body of work, and this could potentially lead to more trustworthy forecasting that would not make people so upset had we come up to see a result that goes otherwise. There are these examples that, again, this is Leo Sella and Martin, Ryan Martin, who pushed the use of IP into supervised learning and to conformal prediction. And also next week, we're going to hear from Peter Grunwald, who is going to hopefully talk about E-values. And these are, real new areas that are kind of at the boundary of statistics and prediction and machine learning that we're seeing IP to emerge. And this is something new. And the last point is something that I hope to discuss towards the end of today, which is the use of IP, potentially the language, as a rigorous way to formulate statistical disclosure limitation and differential privacy, which is something I've been spending a lot of time on these days. So as much as the outlook is very promising for IP because it offers a principled approach to data-driven decision-making, a lot of the work that you're seeing from the previous page, they are done by people who are in this community, and we all know them, and they're all already friends with the IP literature. I really think that IP has more to offer, and more people, statisticians, data scientists, should be using that than what we're already seeing. And I'm, constantly thinking about what are the challenges that would, that are hurdles on the way of making IP more popular and more commonplace in the language of data science. And there are two things that I think about, and I want to talk about them a little bit today, just to frame what I think are important things that the IP community would have to think about in order to popularize and to push for more innovations in this field. The one thing, the first challenge, in which I think is more on the conceptual level, which is that IP models really sometimes can defy the intuition that we derive from using precise probability models, which is right now still the dominant kind of uncertainty reasoning tools. So, again, this is thinking about coming from a statistician's intuition. If the statisticians ask the question, what is theta? Theta meaning some kind of an unknown quantity of interest. And if the statistician utilizes some kind of an interval to report the inference, let's say this is lower bar P and upper bar P. Now, what does the statistician mean by this interval? Now, of course, this depends on what we mean by that interval. And a lot of times the interval in statistics takes on the following several meanings. Most frequently, people think about an interval as a confidence interval. This derives from frequentist statistics. And I would say the majority of statisticians would naturally put their mind to thinking about this being a confidence interval. Or if the interval represents some kind of a calibrated Bayesian posterior interval, which is a Bayesian credible interval, really is something that is expected to have frequentist confidence properties. Or if you do IM, then thinking about this interval potentially as a predictive random set coming from an inferential model, then what is meant by reported interval is that the interval would have to have a coverage probability that is ideally at and never below the reported nominal level for every value of theta that we could envision theta to be. And coverage probability is this concept that talks about repetitions of repeating the sampling procedure and obtaining another sample that is a replication of the current one that we have at hand. This is something that a Bayesian would find a little, to object to, because it kind of invokes this idea of a replication that is nevertheless kind of counterfactual in nature. But this is nevertheless what the language that most statisticians are comfortable with. And in addition to the coverage probability, a lot of times it is also implied that this interval is short, measured, let's just say using Lebesgue measure or some kind of measure. And also that it is sensibly constructed in the sense that it is connected is bounded, it doesn't have holes in there ideally, or that it somehow has a good interpretation that is not going to throw people off in some kind of a corner case logical way. So this is implied that this interval is constructed in a way that is comprehensible and efficient to the best of the statistician's ability. This is usually the interpretation that's attached to an interval as a summary of uncertainty quantification. Now, the unfortunate part about this is that these interpretations do not fare really well when the interval is derived from a creedal set, as we commonly encounter, for example, in robust Bayesian inference. So the reason for that is that when we talk about the lower P and upper P, if they represent upper and lower probabilities of a set, then what we mean by them is that they are bounds. If we have a set of probabilities that we are willing to entertain, and these lower and upper probabilities are the minimum and maximum probabilities that essentially we are willing to attach to a event. So I have given this example many times, and it's really quite interesting and simple, because this is representing, if we have some kind of a survey which is really just a 2x2 table about did you injure yourself on the snow last season, thinking about snow sports surveys, and also do you ski or snowboard, being assuming that there are only two kinds of sports that people play on the snow. So this survey, having these two binary questions, are meant to elicit just a 2x2 table as responses. But suppose that in reality, we always encounter these kind of partial non-response when people sometimes only answer one of the questions, or if they don't return the survey at all. Then what we're left with is an empirical distribution over all enumerations of subsets of these 2x2 4 elements. And if we want to utilize these empirical histogram that is kind of partially coarse to answer questions about, let's say, the injury rate, then we are left with a lower and upper probability, which are just the minimum and the maximum possible rates that this empirical table would imply had we try to imputed the missing answers in ways that would push these two probabilities into the extreme. So in this particular numerical example that I have, the lower probability, the empirical one that's observed, is really just 0.3. That is, if we tabulated all of the yes answers to injury, the certain yes answers to injury, that is as low as 0.3. And if we assume all non-responses of injury to also be in yes, then the upper probability of injury rate goes all the way to 64%. So there is a gap in between that. These really reflect a kind of a bounding operation by finding the probabilities that are consistent with the specification at the extreme values. Now, if the trouble really comes in once we start to try to update and try to do conditioning based on uncertain information and imprecise information. Now, instead of thinking about just the injury rate marginally, what if we try to ask for injury rates that are specific to skiers and snowboarders? So what we're trying to do really is try to do conditioning. Now, the generalized Bayes, I have the asterisk here to talk about conditional probabilities here. What we're really doing is a very sensible one. This is really just to think about all the conditional probabilities of injury given a person is a skier or given a person's snowboarder. What are the respective lower and upper probabilities attached to that? And we can also calculate these, and these things will be well defined just according to, again, this empirical table in front of us. But the one problem that this results in is the issue of dilation. What this has meant is that if we look at the numbers that are reported as the lower and upper probabilities, once we start to condition on this person being either a snowboarder or skier, the lower and upper probability interval, regardless of whether the person is a snowboarder or a skier, becomes wider than the marginal probability interval for just the injury rate. In other words, the upper and lower probabilities for the injury event dilates, and regardless of the conditioning event, regardless of whether we're thinking about a snowboarder or a skier, bearing in mind that these are the only two possibilities for a person to take in this particular setting. So dilation is something that Teddy and Larry back in 1993 defined properly. This really is just talking about that if we have a set of probabilities, and if we think about the conditional upper and lower probabilities of an event giving another event from a partition, then if, regardless of this partitioning event's value, this conditioning lower and upper probabilities will become wider than the marginal lower probabilities, then we say that this partition dilates this particular event A. And I have this kind of a augmentation here about the dilation with respect to a certain updating rule, because you know, we're going to think about potentially using something else. But the most general rule, again, is the generalized Bayes rule that we have seen before. What we are doing is really just taking the infimum and supremum over the possible conditional probabilities that is implied by this set of probabilities that we entertain, which is something that is used in robust Bayesian inference. So dilation is something, and I imagine that, Teddy, you can tell me if this is otherwise. When you wrote the paper, this is of course something that was strikingly strange. So I cannot poll the audience really effectively because this is an online talk, but I have asked this question to many people. How do you feel about this concept of dilation, this effect of dilation? Do you like it or do you hate it? Do you find it great or do you find it weird? You can tell me how you feel about it later, but the one thing that I will say at the outset is that dilation is not a violation of Bayesian coherence. There is nothing wrong about dilation as a matter of something that counteracts or as a violation of the internal consistency of the logic of Bayesian inference per se. But for most statisticians who have encountered the phenomenon of dilation, they find it troubling. And the reason really is just because it creates the sense of a loss of precision for apparently no good reason. Why is it that regardless of conditioning on anything that seems like the lower and upper probability intervals become wider than it apparently is, and, you know, even though we have not really learned anything from the data itself? And if we anticipate dilation, should we go ahead and collect further data, knowing that it's only going to make our interval wider? And remember that wider doesn't mean better in the statistician's language, right? We always want something to be short and to be concentrated and to be precise. So I do have to say that a few of the statisticians do find dilation appealing, and sometimes, and these tend to be the Bayesians who are frustrated with the fact that Bayesian models can only learn and never unlearn. So they tell me that sometimes this seems like a good idea for the Bayesian model to kind of step back a little bit. But most people would find dilation a troubling phenomenon. I was really troubled by it, and this is one of the first things I did as a student. I started thinking about the implication of dilation, and I started to think maybe this is something wrong with the generalized Bayes rule, because it was trying to do this thing that tries to, you know, go out and try to find the boundaries of its own possibilities, and you know, this is what caused dilation, which is undesirable. And there's something else about generalized Bayes rule that really unsettled me as well, which is this, again, a interesting fact, which is that the generalized Bayes rule cannot sharpen a vacuous prior. That is, if we start by specifying our lower probability to be 0 and upper probability 1 for everything, then there is nothing that we can possibly observe to use the generalized Bayes rule for updating to arrive at anything that is different from the vacuous prior. Now, this again sounds like a strange thing to ask, but again, this is one of the holy grails of statistical inference, right? To perform Bayesian inference without having to specify a prior. And this is what prompted Fisher to entertain fiducial inference, which is again an entirely troubled body of work, but then again, it kind of inspired a lot of things that are related to that went into structural inference, functional inference, and Art Dempster's Dempster-Schaeffer theory of belief functions, and later on inferential models. And these things all have some kind of fiducial flavor to it, and everything came from thinking about perhaps one day we could do learning without having to specify a prior. But generalized Bayes rule is not able to do that. And these two things prompt me to think, is there something else that we can do to overcome these weaknesses of this particular way of IP reasoning. And at the time I was studying with Art, and Art's Dempsey rule of conditioning is something that is different from the generalized Bayes rule. And for one, if you look at the shape of the definition, it is already different. It's motivated in a completely different way, but it does result in different answers. And in fact, the good news is that Dempsey rule, it dilates less often than generalized Bayes rule. Every time Dempsey rule dilates, the generalized Bayes rule must dilate, but not vice versa. This seems like a good idea, but then what I end up realizing is that it also creates all sorts of other problems, because generalized Bayes rule is not going to do other weird things. It is still squarely consistent and coherent. On the other hand, Dempsey rule, again, if we take those sort of intervals of probabilities as betting rates, then Dempsey rule is capable of delivering things like contraction, things like sure loss, that would essentially make the agent someone who would lose money for sure. And this is not going to be something that could be admissible, essentially, as an updating rule. So it just looks like there's a grim picture over here that the generalized Bayes rule and Dempsey rule seems to be doing different things, and they can be undesirable under one criterion, but not really the other. And this is really what I have come to realize, which is that when I have these cross marks and check marks in front of these properties, I'm really talking about these properties and assessing them from a statistical point of view. We don't want dilation because we want precision. We want to be able to learn out of nothing, and so on and so forth. But if you think about, again, from a coherence point of view, all the weakness is their strength. The strength is a weakness. And really, because those two kinds of views have, they really want different things, and they prioritize different things over the other. So this is a contrast that doesn't seem to easily go away, unfortunately. So I have come to just think that this is one of the great challenges, which is that IP models, regardless of what we do, even if we go about choosing different kinds of updating rules, and even different decision rules for IP, right? That it would still defy our intuition that is derived from precise probability models. And Gregory Wheeler, in his comments to this work that Charlie and I did, he wrote that trouble for imprecise probabilities rarely comes in the form of inherent contradictions, but instead is more apt to arise from seeking to preserve consistency at all costs. And this seems to be the take-home message, that when we do IP, we really have to balance this idea, or rather, perhaps not balance, but rather to reconcile this sort of consistent-seeking behavior IP, and how do we really communicate that to an audience who is already thinking in a different way, that on certain quantification, the goal, and perhaps the holy grail there, is to in fact make things more precise at the expense of perhaps sometimes making errors and making a fool out of ourselves. So that is challenge one. And the second one, I will use two slides to really talk about. This is what I think is really, even harder of a problem, and perhaps more prominent, which is IP models can be difficult to compute. When I talk about computation versus IP, again, this is motivated really by my background working in the DS theory, the Dempsey-Schaeffer theory of belief functions, which is something, again, I remember this is what Teddy said to me, and I found it, really interesting of a comment, that belief functions is already regarded as one of the things that are more conducive to computation within the IP world. The Dempsey-Schaeffer theory, it has over the years found many successful implementations in computer vision, in signal processing, in artificial intelligence. And a lot of the problems it is used to address have a feature, which is that their state spaces are discrete, and a lot of times finite and quite small, in that, it's really something that a computer could easily enumerate. But, Art Dempsey is a statistician, and his vision for the DS theory has always been within the confines of statistical inference. But unfortunately, statistical applications of the DS theory so far has been quite limited, and typical inference problems, and this is the reason why that is the case, is that typical inference problems, be it parametric or non-parametric, usually would have a continuous state space. And when we talk about upper and lower probabilities and random sets on continuous state spaces, things just got much more complicated. And I will give you one example, and this is just to illustrate how hard it is that we want to perform multinomial inference. This is something that usually, as a ordinary Bayesian, this is something that people can do, as a no-brainer. But if we want to do prior free multinomial inference, suppose that we have observed data that falls into, k different categories, and we have observed their counts. We want to make inference about the relative propulsion parameter, which is just this vector of theta that add up to 1, as well as, be able to make inferences or predictions about future observations without specifying prior on theta. What do we do? And there are several IP solutions. And one of the earlier ones that I've come to know is indeed that was proposed by Art, in a series of papers spanning the 60s and 70s, in which he talked about what is called the structure of the second kind. And it is the multinomial inference model that essentially translates into instead of a random Dirichlet distribution in the regular kind of Bayesian approach, it is a random set that is distributed in the simplex. This is something that has not really been amenable to computation, unfortunately. And after that, there are very notable models that were proposed, and perhaps the most notable one is the Imprecise Dirichlet model, Wally 1996, in which the thought essentially is to think about that there are perhaps S numbers of hidden observations whose value are unknown, and using that as a tuning parameter, the number of fixed and unknown hidden observations, we could derive these this is a typo, it has to be an upper bar here for obvious reasons, that there are a lower and upper probability intervals that represent our probabilities for the next observation falling into the J category, which happens to also be just the posterior mean for theta j given the observations. You can see that there's a gap in between these two values, and the size of the gap is controlled by the specification of the S. And this IDM model actually plays a special role and has a special interpretation when we kind of look at this from a privacy point of view, but I'll talk about that just in about 10 minutes. And there are also other models that are proposed to solve this multinomial inference model. And the notable one is the Dirichlet DSM, and this is Lawrence and Tran Hai is one of the authors. And one of the motivations for both, in fact, at the IDM and the Dirichlet DSM, there are many other reasons to motivate them, thinking about symmetry, thinking about invariance and so on. But both of these models admit analytical solutions to the upper and lower posteriors, which make them a lot more easier to think about because we don't really require any kind of heavy computation to get the results. Whereas the Dempster's model has never really been implemented since it was proposed until recently. And this is something that I was really fortunate and happy to be part of, in which we, in a paper last year, we devised a Gibbs sampler to sample from this 50 years old model that was proposed to conduct Dempster-Schaeffer inference for multinomial inference without a prior. And I won't go into the detail of this other than to say that this was something that I presented as a poster in the last SIPTA meeting. Was online. I wasn't able to be there in person, which is a shame. But if you look at what we have done, it really was a very, very small step. What we were able to achieve was to perform multinomial inference for a moderately sized problems. That's fine, but the model has been proposed for 50 years, and just now we're catching up on making it possible. And this has lagged behind many of the Bayesian Monte Carlo advances that started from back in the 90s. And we really have a lot of catch up to do if we want to put these IP solutions at the foreground and something that people would naturally inclined to use as a tool from their quiver. So this is the second thing I want to say. And I think the fact that IP models may be difficult to compute is something that is particularly paralyzing of its popularity. A lot of times, especially the more pragmatically oriented data scientists, would really, sometimes they think less about coherence in these things, but they want to see the answer. They want to see a solution, and then looking at the solution, looking at how easy it is done, and all things considered, and decide whether this is a appealing method to use. So I think I do really want to advocate for more of us in the IP community to think about how to make inference computational, our packages and these tools readily available for people to try out things that we design and things that we hold so dear as principled approaches to inference. And I don't want to stop there. Of course, I wanted to also talk about opportunities that arise coming from thinking about how IP could help with new questions that arise in the broader scheme of data science these days. And I wanted to talk about one of them, and I have time for really just one of them, which is when IP finds its way into formalizing and rigorously talking about statistical disclosure limitation and differential privacy. And I see that Jay Kadang is in the audience. And I met Jay when I was in my last year of PhD studies, and the one advice that Jay gave me at the time, I feel like I can say this now, that is that at the time I was really all of my time was spent on thinking about foundations, thinking about IP, thinking about denser safer theory, and Jay said to me that get a day job. By which is meant that there is a lot more the statisticians can do, in particular perhaps on the applied side, on the more immediately useful side, that we wanted to sort of expand the research repertoire into something else, and I did, and differential privacy really is something that I have spent more of my time on these days, and in a way that is not directly related to IP for the most part, but I have to confess that I went into this field really because of the connection from IP, and this is something that I want to talk to you about because I really wanted to get you all excited about it, and to explain why that IP could help in framing the needs of privacy and this inherent desire to preserve information, to withhold information for the purpose of guaranteeing the confidentiality of individuals. So and privacy as a new challenge, I would say, in modern data curation arises particularly as our ability to store data, to collect data, and to disseminate data has skyrocketed over the past many years. And a lot of times previously, a lot of these things were not so much of a concern, but recently, if you think about what the data curators do, and by data curators, what I mean is perhaps thinking about official statistical agencies as well as corporations, Google, Apple, Facebook, they really seek to do two things at once. The primary goal, a lot of times, of course, is to collect data from the data users, and they want to be able to do that well. They want to be able to compile and produce data products. These are summaries and reports and key statistics, and they want to be able to disclose that to appropriate users and to meet the demand for particular use cases. But at the same time, they really are required, sometimes by law, sometimes by policy, GDPR, to protect the privacy of individuals. And they want to do that with some trustworthy guarantees and to fend off adversaries and people who are peeking into people's individual private matters. So one primary example and something that has motivated a lot of my current work is the use case coming from the Census Bureau. Now, the US Census Bureau bears the constitutional mandate to enumerate the population living in the United States every 10 years. And this number is going to be used for apportionment on the assignment of House seats to the different states. And the last census really was the 2021, so 2020, so 2 years ago. And at the same time, the Census Bureau is also bound by what's called the Title 13 of the US Code to protect the respondents' confidentiality. And the Census Bureau has always had in the past some kind of a privacy protection, or rather they call it statistical disclosure limitation techniques in place, but they weren't as rigorous or as provable or nor as transparent. And for the 2020 census, the one that just happened 2 years ago, the Census Bureau decided to adopt what's called the differential privacy as this new disclosure limitation guarantee, and to utilize that to protect the data products that's being released. And I wanted to tell you about, if you want to read further, this is a recent, very, very recent, it was launched just last Friday. It's a recent special issue by the Harvard Data Science Review. The link is on the bottom. This is a special issue that, particularly to feature the technical document that was written by the Census Bureau's own team for disclosure avoidance to discuss the design of what's called the top-down algorithm. And this is the algorithm that protects the data products that they put out for reapportionment purposes with differential privacy. And this you can find on the Harvard Data Science Review front page. And this special issue also comes with a whole lot of other accompanying articles that are that span from empirical evaluation of the effect of privacy protection to talking about the consequences, and to talking about how over the several years of its making, how things have evolved, and the social scientists' reactions, demographics' reactions, and things and all kinds of issues around that. So if you're interested, I really highly recommend that you give the review a look and to check out some of the things that are published there. But I want to talk about, again, coming back to our my goal here, which is to try to show you why IP could be helpful in differential privacy. Now, this really we have to start from explaining what is the mechanism of differential privacy. What does it do to the data? So differential privacy, the goal of differential privacy is to somehow enable the data user to learn about aggregate features of a database, at the same time protecting the privacy of individual respondents. Those two things seem to be at tension with each other, and this is where a trade-off would have to be drawn. So what is differentially private? The thing that would be called a differentially private mechanism is in fact a random function. This function takes in a database, which is here denoted as X, and also takes into itself essentially a noise. This is going to be a very carefully crafted noise. So this T function here is now going to be a randomized function where the randomness comes from the R. And we say that the randomized function T is epsilon differentially private if for all neighboring databases, X and X prime, which are the same everywhere else except for just one record, that's what means they're neighboring. If for all neighboring databases, X and X prime, and all measurable sets S, we have that the probability ratios between that's induced by T as it is applied to X and as it is applied to X prime are very, very close. Close meaning that this ratio is always everywhere bounded by exponential epsilon, where epsilon is a small positive number. Now, in extreme case, when epsilon is approaching 0, you can see that essentially what this is asking is for the probability ratio to be 1 everywhere, in which case there's only one possibility, which is that the distribution of T as it is applied to X and as it is applied to X prime are exactly the same, which is really just to say that by looking at the distribution T, there is nothing that we can tell about whether this function was computed from X or X prime, being two neighbors and they're different by only one person, which is just the smallest unit of privacy that we care about here. Now, as epsilon become larger, this probability ratio will become wider, and there's less control over how different they can be. And there will be more information coming from looking at T to be able to tell whether it was computed based off of X versus X prime. Now, essentially what differential privacy mechanisms do is that they conceal the confidential database by infusing some kind of a crafted noise. This has to be a carefully designed noise into the data product. So this has to be, say, T, and this T is something that is released to the public. And one of the most commonly seen, one of the earliest mechanisms of differential privacy really is just is an additive one. We compute a query, and let's say the sum of a bunch of numbers or the mean or its variance, and we add a Laplace distribution whose scale is inversely proportional to epsilon. Now the epsilon is called the privacy loss budget. The more of a privacy loss budget, the more privacy we could afford to lose. And for that, a smaller scaled noise is added to the query. On the other hand, the smaller the privacy loss budget, the less privacy we can afford to lose, the larger of a error we must add to the query. So we can see that here there's a privacy utility trade-off, which is that the smaller the privacy loss budget will lead to more privacy, but it gives rise to larger noise, which translates into less utility because, again, if we want to observe something, ideally we'll want to observe it with as little noise as possible. So this is the design of differential privacy. And the key here is, first, someone would have to design how to infuse this crafted noise. And second, and this is very much a policy decision, how to decide what is the right privacy loss budget to use for this data product that is to be released. So I will tell you how can IP help in this entire frame of differential privacy, which is something that has already been seeing very impactful applications in privacy protection in official statistics and in corporations use in behind the data storage and dissemination, Apple and Facebook and LinkedIn and so on. There are three things I want to tell you about, and there are three paths through which IP can help, and through one of them, which is what I will talk about next, I will explain to you, in fact, how I myself came to even look at privacy, which is really through this connection to what's called internal measures, which I'll explain in a bit. Well, the first way out of the three I'll discuss today, in which IP can help in differential privacy, is that IP really supplies a rigorous vocabulary for describing the kind of data imprecision and inferential imprecision under privacy constraints. Now, there are many examples, and I'm just taking one out. If we look at the imprecise duration model, again, this is something I showed earlier, and suppose that there, the parameter of the hidden parameter S is set to be 1, which is something that Wally, in fact, talked about in his paper to say that this is a very common choice. And this really just means that we have one hidden observation whose response is something that we do not know. Then the lower and upper probabilities for the future observation or for the posterior lower and upper probabilities for theta really is, on the one hand, just the number of number of observations falling into the J category over the total number of observation plus 1. And the upper probability is nj plus 1 over n plus 1. If you look at the difference between those two, what this really is showing is that we have this one hidden observation S being 1, and we just don't know whether it's a 0 or a 1 as a response for being n of j. This makes an implication of the underlying database in that we did not know which one, and they differ. The two possible databases that could have they could have given rise to these lower and upper probabilities if we were doing precise probability calculation, is that the two databases were different by exactly one observation. And this is exactly the notion of a neighboring database that arises from differential privacy. If we set S to be a different value, then this ideally would be incurring some kind of a group privacy. So that not only are we thinking about the difference between just one individual response, but S different responses. But there is a very close alignment between the language of IP and how differential privacy describes its privacy guarantee as a bound on neighboring databases. Now, the second one is the interval measures, which is really something that how I came to into this DP world. And the interval measures is a IP object. It's something that was discussed in first, I believe, in the Roberts and Hartigan paper in 1981. And what it is that it is, as it suggests, it's an interval of measures. And now, if we think about two measures, sigma finite measures L and U, and think about all of the measures, the convex set of measures, so that they are sandwiched in between this L and U, then this collection, this convex set of measures, is called an interval of measures. And the lower bound L and the upper bound U are going to be called the lower and upper measures, respectively. Now, interval measures, they can be used to describe robust neighborhoods of sampling distributions. These are objects that could be used to talk about whenever we have an uncertainty about where the likelihood arises. And this is one of the examples that Mike Levine talked about in his paper in 1991. It was talking about sensitivity not only in robust Bayesian inference, not only against prior uncertainty, but also about the sampling uncertainty. And Levine has this recursive algorithm that could help to compute various upper and lower posterior quantities when the sampling distribution is uncertain and takes the form of an interval of measures. And in particular, when the lower and upper measures, L and U, have densities with respect to some kind of a sigma finite dominating measure, then this interval of measures defines a density ratio class probability neighborhood. And density ratio classes of probability neighborhoods are wonderful. They have many interesting properties. They're invariant with respect to Bayesian updating, so they remain density ratio classes if we keep doing Bayesian updating using a generalized Bayes rule. And they're also immune to dilation. They just don't dilate. And this is something that was discussed in the original Seidenfeld and Wasserman paper. Now, what does this have to do with privacy is that if we put the definition of epsilon differential privacy and the definition of interval measures side by side, what we realize is that epsilon DP really could be represented as just interval measures. This is precisely the language that's needed to describe it. In particular, if we think about X and X prime, these are databases that are different by only one. These are neighbors. Their Hammond distance, their Hammond distance is 1. Then the measures that are induced by applying this random function t to x and to tx prime is such that they are respectively, the measures that they respectively associate to, the p and q, would have to be bounded by one another, in the sense that the lower and upper probability measures, when you inflate it and deflate it by a factor of exponential epsilon, it creates the interval measures that bounds that of p. And in particular, if, again, p and q have densities, which is often the case that we encounter in applications, then these densities, small p and small q, really have the property that, the density of p is going to be bounded by a factor of plus or minus exponential epsilon q of t. And this, again, if you compare this expression with the expression that is the ratio that is bounded above, it is really what epsilon differential privacy is talking about. So, again, thinking about, what this language can help us to understand is where on the spectrum of the privacy and utility trade-off are we sitting? And I really, this is on the right-hand side, this plot is something that was using Levine's algorithm to try to, this is an illustration essentially about the bound of the posterior predictive upper and lower probabilities for having given an observation, and what does it imply for a future observation. And you can see that with different implications of a choice of a privacy loss budget, the width of the interval are really different. When epsilon is 0, meaning that there is no privacy to spare, we have to protect everything entirely, then there is a lot of information that comes from observing one observation and what can it tell about the other. In that there is, it has to be, the two distributions have to be identical, and there is nothing that is that's contained in the observed posterior that could be used to distinguish from the current observation from a adjacent observation. On the other hand, if the epsilon is slightly larger, there's a lot more room essentially for the two posteriors to differ, and this wider interval represents a possibility for more information to come in, because the two adjacent neighboring databases would have the ability to incur different distributions that are much different from one another. And this is really to say that this complements our understanding from using privatized statistics to draw inference, which is about a unknown quantity that is out there, which is of our interest, which is, in general, what happens is that the more privacy loss budget that we could spare, meaning that the less, the more privacy loss budget that we can spare, there's more data utility coming from it, and there is more to be learned from this observed privatized statistic, and there is more precision coming into the posterior that would, but in general, the privatized inference is going to sit somewhere in between. It's going to sit in between the posterior inference that we could possibly obtain from a precise statistic and that coming from nothing at all, namely that we have just the prior. It's always going to be somewhere in between. So this is one way that IP could be used to formulate this rigorous vocabulary for the information coming from privacy constraints. I will talk about two more. I will not go into details. I'm also running out of time here. And then one of them, the second one I would like to talk about is that IP could be used to draw principled inferential conclusions from privatized data, especially when the privacy mechanism itself is not transparent. And this would take an entire whole talk about the relationship of transparency, how that is important for statistical inference. The take-home message is that when we move to differential privacy as a disclosure limitation guarantee, the one thing that it brings to the table, and something that was never here before, is that it brought transparency to the privacy mechanism. We can talk about the privacy mechanism and its design without sabotaging the privacy guarantee. And this is something that is really wonderful about differential privacy. However, when that promise meets practice, a lot of times this transparency itself is not something that we could take for granted. A lot of times the privatization scheme can be sufficiently complex, even though transparent but sufficiently complex, or that it was pushed through some kind of algorithmically defined post-processing to a point where what we are left with is just a whole black box of things that's done, even though described, and perhaps the only thing that we can rely on coming from the privatized data is only that there is a bound on the information content that is coming from the privacy guarantee on its own. And in these situations, instead of trying to make a precise model out of the privacy scheme, what we can do is to use IP to talk about the bounds that could be achieved, the upper and lower probabilities that is coming out of making inference from this privatized data, where the only thing that is known about it is that it is the fact that it is private, and there is no transparent information about the privacy mechanism itself. And The last thing, which is also something that is very recent, it was brought to my attention because it's not, this is really also kind of a work that is just emerging at the intersection between econometrics and differential privacy, is that there are special cases of the privacy mechanism because of the circumstances of its application, and because of stringent settings of the privacy loss budgeting policy. It could in fact result in the non-identification or the partial identification of parameters of interest. Now, I have to clarify that this is not the intention of differential privacy to begin with, but it could sometimes arise due to extraneous reasons, such as, I would rather not go into them, but clamping and things that people must do to modify the mechanism to suit particular purposes. And these are things that might go and give rise to non-identification. And one of the recent work on this is the Komarova and the Kipelov. These are two econometricians that wrote this paper that is talking about identification and formal privacy guarantees. And what comes about from there is that you can see that sometimes under very stringent conditions, what could result from the model could be a set model. And this is essentially something that is represented as a belief function or as a random set. So if you're interested, I have the bibliography at the end, and this is something that please go check out. So that brings us to a close. It was a lot of things that I said today, and they're a little they're really kind of three parts. I talked about kind of two challenges and one really promising opportunity, which is still at its infancy, and I would hope to get more of you excited about it. And to summarize, I think IP holds great promise in data science. I think it should be more popular than it already is. And I think the three things that we can do to make that happen is to first think about how to reconcile IP reasoning with the existing intuition that people derive from having been so accustomed to using precise probability models. We must think about how to develop accessible computation techniques for even just moderately sized applications. We're not even talking about huge databases and so on and so forth, but moderately sized ones. And the third thing, which is something that I have, I hope was sufficiently interesting to you, which is that I think that we should explore and even exploit this natural role of IP in discussing privacy, in statistical privacy and differential privacy, because they're the goal, the ultimate goal is to conceal information, that it just goes so well with what IP as a object is apt to do. So thank you very much. If you're interested, I would be so happy to talk to every one of you about these more. You have my email there, and I'll be happy to take questions.